I'm going to talk about the method of separation of variables. I'll assume that you know what a differential equation is. If you don't, I would invite you to watch my introductory video. So, the method of separation of variables is used to solve differential equations with the following form. So you should be able to isolate the derivative on one side of the differential equation, and on the other side you should have a product of two functions, and each of those functions should be functions of different variables. In this case, the variables are x and y. All right? So let me show you how to derive the formula that we will use to solve such differential equations. Let me divide both sides by the function g. Now let me take the antiderivative of both sides with respect to x. All right, so far so good. Now let me simplify the left side by using the method of u substitution. So let's let u equal to y of x. So in that case, u prime will equal y prime. And that implies that the left side is equal to the antiderivative of 1 over g as a function of u with respect to u. And that is still equal to the antiderivative of f of x with respect to x. Okay? So on the left side, I originally had x and y, but because of u substitution, I was able to make the left side in terms of the variable u. Now, would you agree that the name of the variable u is not relevant? I could have also called the new variable v or w or a or b or c. Okay, it really doesn't matter. In fact, because it doesn't matter, I can choose to rename that variable u to something else. I can even choose to call it y if I wanted to. And in fact, I will do that now. All right, so there is the key formula for the method of separation of variables. Okay, please make a note of that. We will take two antiderivatives, and each of them is with respect to a different variable. All right? Now I'm going to show you an easy way to remember this formula. So let me rewrite the original differential equation as follows. So I'm rewriting the differential equation, substituting dy over dx for y prime. They both mean the same thing. They both mean the derivative of y with respect to x. Okay, so to see what that key formula is, one way to arrive at it is to assume that you can treat dy and dx as regular variables, that you can treat dy over dx as a regular fraction. Okay, assuming that that was the case, let me show you what happens if I move terms around, okay, using the rules of algebra. So I could move the function g to the left side by dividing both sides by g, and I could move the dx to the right side by multiplying both sides by dx. Okay, and then I could take the antiderivative symbol and put it at the beginning of each side of that equation, and that's one way to arrive at the key equation that I derived on the previous board. Okay? Now let me do an example exercise using this method. What if I had the differential equation y prime equals a constant times y itself? Now, you may know that the solution to this differential equation is an exponential function, but let's pretend we didn't know that, and let's see what the method of separation of variables will give us. So I will move the y to the left side, and so I'll have to take the antiderivative of 1 over y with respect to y, and then I will take the antiderivative of a constant with respect to x, right? That's the application of the key formula for this differential equation. So now I can take the antiderivative of both sides. On the left side, I'll get the natural log of the absolute value of y. On the right side, I will get k times x. Now, both sides will have a constant of integration. I can combine both of them into 1. All right. I could conceivably have the sum of, or difference of two constants, but that itself can be replaced with a new constant. Now, what I can do is I can treat both sides as the exponents of e. So I get e to the ln of the absolute value of y equals e to the kx plus a constant. Now, the left side simplifies to the absolute value of y. The right side can be written as e to a constant times e to the kx. Okay, the effect of the absolute value function is either to do nothing or to multiply y by minus 1. All right, both of those are just effectively multiplying y by some constant. So I can divide both sides of the differential equation by that constant. So in other words, I can just put a plus or minus in front of the e to the c on the right side, and that'll serve the same purpose, the same function. All right? So e to the c is just a constant. Plus or minus e to the c is just a constant. Why don't I substitute another constant for that constant? Let me call plus or minus e to the c the constant a. All right, and lo and behold, there is our general solution. Okay? And we arrived at that using the method of separation of variables. Okay? Let me do another example. Let's solve y prime equals x times y. So using the key formula, I have to take the antiderivative of 1 over y and set that equal to the antiderivative of x with respect to x. On the left side, I will again get the natural log of the absolute value of y. On the right side, I'll get x squared over 2, and I'll combine both constants of integration into 1. Now, once again, I'll make both sides the exponent of e. Okay, so the left side again simplifies to the absolute value of y. On the right side, I can rewrite that as e to the c times e to the x squared over 2. And I can remove the absolute value function and just add a plus or minus on the right side. And I can replace plus or minus e to the c with another constant. We'll call it a again. And there is the general solution. You can take the derivative of the general solution to convince yourself that indeed it does satisfy the original differential equation. Okay, that would be a good idea if you're skeptical. Now let's have you try an example. Would you please try to solve this differential equation? Y prime equals y divided by x. So pause the video and you try to use the method of separation of variables. Okay, so I'll go ahead and do it now as well. So I'll take the antiderivative of the reciprocal of y and the antiderivative of the reciprocal of x. I'll take one of those antiderivatives with respect to y and one of them with respect to x. So I'll get a natural log on both sides. And again, I'll combine the constants of integration. Now I will make both sides be the exponents of e. So the left side simplifies to the absolute value of y. The right side simplifies to e to the c times the absolute value of x. And that's equal to the following equation. Y is equal to plus or minus e to the c times the absolute value of x. And in fact, I could multiply the right side by either plus or minus to do the equivalent operation that the absolute value operating on the x does. So all of that is to say that I have plus or minus e to the c times just x by itself. Okay? And again, I will replace plus or minus e to the c with another constant. So y is equal to a times x. So that's just a line, nothing more than a linear function. The graph of that is nothing more than a line, I mean. Okay? And again, I invite you to take the derivative to convince you that indeed it does, it is a solution to the differential equation. Now I'd like you to do a slightly more challenging example. Would you please try to solve y prime, the derivative of y equals x to the 8 times y to the 12. And this time, I don't want you to find the general solution. I want you to find the specific function that satisfies this differential equation, and y with respect to x equal to 0 is, I want the solution to have y of 0 equal to 3. Okay, so can you solve this one? So pause the video and try that now, please. Okay, so I'll go ahead and do this. So I will take the antiderivative with respect to y of 1 over y to the 12. And then on the other side of the equation, I'll take the antiderivative of x to the 8 with respect to x. So the left side will simplify to y to the minus 12 plus 1 divided by minus 12 plus 1. The right side will simplify to x to the 9 over 9. And then we'll combine both constants of integration into 1. And so let's see, we've got on the left side minus 1 over 11 times y to the minus 11, and that's equal to x to the 9 over 9 plus c. Let's see, so now why don't I try to solve for the constant of integration? And I'm going to do that by using the fact that when x is equal to 0, y has to equal 3. So minus 1 over 11, I'm going to replace y with 3 now. So 3 to the minus 11. And that's going to equal 0 plus c. So now we know that c is equal to minus 1 over 11 times 3 to the minus 11. And let me multiply both sides of the latest version of the latest equation, the one with the minus 1 over 11 in it, times y to the minus 11. Let me first do this, replace c with what we found it to be. So minus 1 over 11 times y to the minus 11 equals x to the 9 over 9 plus, actually, why don't we make it minus? Minus 1 over 11 times 3 to the minus 11. Okay, now let me multiply both sides by minus 11. So I get minus 11 times x to the 9 over 9 plus 3 to the minus 11. Okay, now to get rid of the minus 11 on exponent on the y, I'm going to raise both sides to the minus 1 over 11 power. When I multiply that by minus 11, I'll get the exponents will multiply to 1, so I'll just have a y. And that's equal to minus 11 times x to the 9 over 9 plus 3 raised to the minus 11, all to the minus 1 over 11 power. All right, and once again, I would invite you to take the derivative of that and convince yourself that indeed it does satisfy the original differential equation.